Welcome back, and we are going to continue our discussion of convergence and divergence of series. And so this week we're going to look at alternating series tests, absolute convergence, and then use that as a way into discussing the root and ratio test. So we have really four tests to discuss in this week, so it's going to be kind of busy. So let's go ahead and get started. So far we have the comparison test, which we discussed last time. We have the limit comparison test, we have the integral test, and each of these have their own suppositions. And then really another thing that we might use to discuss convergence and divergence is the nth term test, which you might have to review your notes for that, but that's just the idea that if the limit of the sequence does not approach 0, then the series is divergent. So that's what I call the nth term test. Now, the alternating series test, we have to first discuss what an alternating series is. And it's just, quite simply, a series whose terms are alternately positive and negative. So, for example, we could have the series, I'm just going to omit the indices for right now, but -1 to the n over n, right? That's fine. We could have series of -1 to the n plus 2, I don't know, all over n squared plus 5n. Okay, that's fine. Something where we don't always get things being positive and negative is something like the series of sine of n. And so that one, it's not always guaranteed to be positive then negative, positive then negative. It has to be every other term alternates. It just can't contain some positive and some negative. Okay, so then when we look within this series, right, we have a sequence, and so we can write the nth term of an alternating series is -1 to the n times another sequence, or n plus 1. It doesn't matter. But we should be able to pull out that alternating component, which is the -1 to the n or n plus 1, and then the non-alternating sequence. And so the non-alternating sequence, we need that to be positive. Okay? And so we want to have all this in mind, and with that we can then formally define the alternating series test. So we have that alternating component and then the positive component, and we would say that this series is going to be convergent if we satisfy two conditions. Well, first, Bn has to be positive. Okay, so that's really like a part 0, is that Bn is greater than 0, greater than or equal to 0. Okay, but the sequence has to be decreasing, okay, similar to the integral test, and the limit must be infinity, or the limit at infinity must be 0, okay? And so when we have that, we're going to have a convergent alternating series. Okay, so the diagram here is, if we're using S and N, and we kind of think that the series is going to sum to S, and Sn is the partial sum, right? When we look, it's going to, first term might be, I don't know, like this, and then when we add, so again, it could start out negatively, but it shouldn't, positive, and then we're going to add a negative, so then it's going to drop a little bit, and then we're going to add another positive, so it's going to shoot up. And then and then we're going to add another negative, so it's going to come down, and then up and down, and up and down, and up and down, and eventually you get to this limit S. Okay, that's the idea of the test. Because we know that the sequence is decreasing, and the sequence also has a limit of 0, so meaning that as we add or subtract, we're actually adding essentially nothing. Okay, so we can easily approach that sum. Okay? And when we look at the proof now, the picture really is kind of the idea behind the proof. What we want to do, and this is just going to be an outline, what we want to do is we want to first look at the even partial sums. Okay, so that is to say, let's look at S2. Well, we know S2 is going to be, according to the definition of the series, B1 minus B2, or it could, be the other way around. Doesn't much matter. Okay, but anyway, we're going to assume that it's this form, and because B2 is less than B1, this is going to be positive. Okay, and when we look at S4, well, this is going to be S2 plus B3 minus B4. Well, that's also going to be positive, right? And so we can continue this way, and really it's kind of like a proof using induction. But when we look at S2n, this is going to be S sub 2n minus 2, and then plus B 2n minus 1 minus B 2n, like that. And all of this, right, if I look at that term, that's still going to be rather small. So, but what we can say is that this is going to be this is going to be bigger than S sub 2n plus, or S sub 2n minus 2. Okay, because we're adding, this difference is greater than 0, so then we're adding on to it. Okay, so when we look at now the sequence of even partial sums, we can say S2 is less than or equal to S4, less than or equal to ... less than or equal to S sub n, or 2n minus 2, less than S sub 2n. Okay, and you can keep on going. Okay, and with this, we can also take a minute to look at S2n in another way. We can say, well, S2n, this is going to be B1, and then now I'm going to just write the sequence in a little different way. Subtract B2 minus B3, and then subtract B4 minus B5, minus ... and then minus B sub 2n minus 2 minus B sub 2n minus 1, and then minus B sub 2n. Okay, so really, we know, okay, this, and we know that these are, the sequence is decreasing, right? So this is going to be a positive value. Each one of these is going to be positive. So then I'm taking B1 and always subtracting it. So I can easily say that B1 is going to be bigger than or equal to S sub 2n. So now why is this important? We have a sequence that is monotonic, right? That's this first part. And we have that the sequence is bounded, right? So a sequence that is bounded and monotonic is convergent, okay? So then that means that by the monotonic sequence theorem, that the limit of S sub 2n is equal to S. Okay, but now this is only the even sums, right? Well, it turns out you can do the odds in a similar fashion. Do odd partial sums similarly. So then we have a convergent sequence. And so then when you sum two convergent series, the result is convergent, so then we're done. Now the book does offer a different ending here. They show that the limit of the odd series, or the odd partial sums, is still convergent in a different way, but at the end of the day, we end up with a convergent thing. So all of this was to, again, prove the alternating series test. We did make use of the fact that the sequence is decreasing over and over. The textbook uses this second part in its proof, so that's why they have that part. And I kind of got around it in my proof. So just know that it does end up being used. Now, we haven't done an example of this. That'll be in the next video, so stay tuned for examples that use the alternating series test to conclude convergence.